India FOSS 2025. We'll start with Jithin, who will tell us about KuttyPy, a zero-cost innovation that transforms the Arduino into data acquisition system for STEM. Thank you.
Thank you for the introduction. My name is Jithin, and I develop data acquisition instruments primarily for science, mostly physics, as well as some other subjects as well. Now, if you're a budding scientist or a citizen scientist, and you wish to collect data about the environment, let's say how humid is this room over a period of time, let's say, then either you go for commercial solutions where there is a probe that measures humidity, maybe you have something that transfers data to your computer, you write some code, etc. But what we're looking at is the lowest cost that you can achieve such tasks. Now, if you're a student, you would probably turn to the Arduino and you would buy a humidity sensor, which will cost you maybe 200 rupees or something these days. Then you would write some code to get the Arduino to read that sensor, relay to your computer. Then maybe you want to write some more code to plot this data, analyze it, etc., etc. So the solution that I'm presenting here is sort of a transformation of the Arduino to include all these data acquisition capabilities to make it something that interacts with your computer in real time, no compiling code or uploading. And how we achieve this is by way of a modified bootloader, which is a fork of the OptiBoot bootloader, which already comes with your Arduino Unos and Nanos. So so on the Arduino board, for those of you who are familiar, you have your IDE, you have some function calls, you compile your C code, upload it to your board, and make it run. Now, in embedded systems, if you are an embedded systems engineer, say, you would use registers, which are basically bytes, where each bit has a function that makes the hardware do something. Let's say I toggle this bit, there will be this output pin where 5 volts or the supply voltage will show up. So it's all binary. Now, what the KuttyPy bootloader does is that it allows you to make changes to this register via a computer that's connected to it. So there's no compiling or uploading. You could write some Python code through its Python library and try to light up an LED, or try to read a register and through evolving complexity try to read sensors, etc. So let me show you a short demo. This is the user interface that I made for the Arduino Nano. Now what I've done is I've replaced the bootloader of the Nano with my own, and this allows me to, for example, PB5 is the onboard LED, and I could check the input state, it's low. I could make it output state, toggle the state of the output, all through Python code. And that library it's documented on read the docs. I'll get to that shortly. So you can see the board here, and as I toggle it, you can see that the onboard LED getting toggled. So it's a very basic implementation that I'm talking about right now. So these are both 328P boards. So the registry structure, everything on the data sheet remains pretty much the same, except the ordering of the pins. So you just change the layout accordingly. It's all documented on read the docs, where you have simple function calls. For example, you can import the library, just say set a value to a register and the board will immediately behave that way, or read a value from the register. And as things get more and more complex, you can read values from sensors. For example, an accelerometer that's plugged in onto this board, or control robots through a servo interface, hall sensors, etc. So there's no coding as such involved here. You have a data acquisition instrument right out of the box by just modifying the bootloader on your Arduino. So how do we do that? Okay, there's a very simple change that has been made. On the Arduino bootloader, the job of the bootloader is to get the user compiled code from the computer, flash it to your non-volatile storage on the processor, and start running it. In the KuttyPy bootloader, you just have a couple of additional calls to read and write registers without actually touching the program space area. Okay, so if you have a parallel programmer, you can replace the bootloader with the KuttyPy bootloader. Or if you don't, you can just turn another Arduino into a programmer, make the following connections. I'll just run through them. It's pretty straightforward. And you can flash another Nano with the different bootloader. Now it continues to run as an Arduino. The remaining functions are already there. It's just that you can collect data with it. Right. So this is just the implementation. On the C side of things, there is a couple of extra function calls on the bootloader that allow you to read and write registers. On the software side of things, what I've done is just read the data sheet, find out the address of these registers. Let's say you're dealing with DDR, or let's say TIFR. So it has a register, hex 38. So you go to that location and read it. Or if you want to write to it, you write to that location. So the bootloader is only being told that go to this location, write this value, or go to this location, read this value. So just as it's basically like a debugger. And there, you've transformed it into something you can collect data with. Of course, you can add more UI elements to make it a more teaching friendly tool for embedded, where we don't use abstraction layers. We directly tell students to read the data sheet where it says, okay, this bit does this. You pick out that register, toggle the bit, and see that the hardware is doing that function. Okay. Now, with this, I picked out a board that is, sorry. Yeah. Now, with this approach, I built another board. All the schematic layout, everything is linked to in my presentation. This uses the Atmega 32 processor instead of the 328P on the Arduino Unos and Nanos, simply because the 32 is more suitable for teaching. It has 4 ports, A, B, C, and D, all of which have 8 pins. So it's more easy to teach because we have complete bytes. And I included included a bunch of LEDs on board, so we can see the changes for an entire register, a whole set of switches, an R2R DAC, etc. So again, this thing will also work with the Arduino IDE as long as you just select the Atmega 32 board. The software can do all these listed tasks. Reading, writing pins, of course, is one. To monitoring sensors, the ADC values, etc. So here, for example, this particular pin, PC3, is configured as an input initially. You could make it an output. You could make it read values. So this is the ADC value. And because everything is in Python, it's quite simple to make data loggers, which of course has already been done for you. And here, this is ADC values being plotted as they're being fetched from the processor. Now this makes it easy for students. For example, if you're building a project with Uno and you don't know if a particular part is working. Let's say I have a robot with a potentiometer that's measuring an angle of some some angle. Okay, and if you don't know if the ADC is working, you would normally bring out a multimeter and measure the voltage at that point. But here you can simply switch to the bootloader mode and quickly check that the ADC values are correct. Or if connected sensors are not functioning or something, you can come and scan for those sensors and check the values here. Okay, now based on this board, I am currently at the University of Calicut, where we're running outreach programs for teaching kids embedded systems. So we have a whole curriculum where we start out with what are decimal and binary number systems, teach them how to convert between these two, then go on to the importance of bits in embedded systems. Then we move on to a whole programming basics of programming, because see their course includes Scratch, but they're as yet not being taught to use them to achieve tasks. So for example, we initially asked them, can you make a multiplication table? So that's really not there. So we have to start with programming. We go to basics of making tables. Then we move on to plotting. It's all done in visual drag and drop form, no C or Python. So they just create logical segments and make some usable things. For example, a water tank. What do you call that? A pump that fills up a water tank and automatically cuts off the moment a pressure sensor reading goes above a certain threshold, and if it goes below a certain threshold, you turn the pump back on. So the basic applications that 8th standard students, 6th to 8th standard students are able to do, to more slightly fun things like measuring your heart rate, or even this Google's MediaPipe library we've embedded into the user interface. I'll show that shortly. 2 minutes. This is just things that we can do with it. There's also an Android app. Android, because Apple requires extra certification, but on Android, since Arduinos is just USB to serial converters, we have this whole UI where you can do everything that the desktop app can do, including C compilation. But because we can't have a C compiler on the phone yet, it sends your C code to a cloud droplet that I have, compiles it, sends back the hex code, and uploads it to your device. Then there's visual programming. This is built on Blockly, and there's a bunch of blocks for toggling bits, reading registers, etc. And for example, if you want to read a sensor, which is this Max 30100 pulse oximeter sensor, has become really cheap since COVID, about 100 rupees. This is all that you need to do. You need like a block for reading the values. You plug it to a plot block, and then you just keep repeating. So you'll get these plot values. As a whole set of sensors that are compatible. Yeah, you can control robots and things. That's the whole list of sensors that so far have been supported. So the device only speaks on the I2C bus. All the sensor specific code sits on your Python library or your Android app. And the code is, of course, since it's Python, it's like 2-3 lines of code just to read information from a particular sensor. So here it's just initialize this TSL2561 light sensor, read the values from it, and just plot it on the screen. So it's like 3 lines of code. Right, I can show you one sensor. So I've plugged in the board with an accelerometer sensor on top of it, which is this MPU 6050. Just go and launch the UI. And here, if I scan for sensors, which is here, I'm sorry. Yeah. So there is a scan button here, which will simply go on the I2C bus and search for sensors that are available. Then you can start fetching readings right away. Now, the usability of this in, for example, a physics lab setting is that you can use Python's libraries like SciPy to extract more meaningful information from this. For example, if this was part of a pendulum and it was oscillating back and forth, let me pretend it's oscillating. Right, so this is GY, you can see the oscillations, and I can pull up the data logger. So where you can visualize these oscillations. Now, if you wanted to know the frequency, you could select a particular sine wave from these. It's not a clean sine wave, but SciPy will still sort of fit something, and say sine fit. There. So I have around 1.5 hertz oscillation frequency, which is extracted from all these data points. And of course, we have demos written where you can programmatically fetch readings and then feed it to SciPy with a standard a sine omega t plus phi function and fit information. So the fit is pretty decent for this sort of poor, noisy data, but it finds applications. So far, we're looking at a very low cost system. Like you have your Nano or your Uno, which is nowadays like 300 rupees or so. You have an accelerometer, again 150 rupees or so, and you're already looking at digitizing readings from a pendulum and getting second or third decimal precision when it comes to time period measurement. In your schools, you have this simple pendulum where you use a stopwatch and you take 20 oscillations and you still end up with barely first decimal precision. So this gives you much better control, much better automation. And there's also an IDE which is very basic at the moment. I still need to work on it. Which has we wrote a bunch of examples which focus on registers, right? Instead of having digital write, digital read, things like that, you go and say, okay, DDR pin B ampersand whatever masking that you're going to do. So that's there. Then there is your visual coding, which is, like I said, based on Blockly. So here It's pretty simple. Read ADC from A1, plot versus time, to it 200 times. So when you run that, you're actually getting the plot of noise from the ADC. This is sort of a work in progress, but I think sensors. Yeah, so if you were to deal with sensors, not sure this works yet. Yeah. When I click the scan button, the sensor was detected. Now I can select the parameter that I want to log, for example, GZ, or I'll say GY. And say, so now it's recording values from the accelerometer in my hand. So this is all part of the series of workshops that we conduct for school kids to get them more interested in this sort of thing. Right. And we have a bunch of sample programs for different things. Okay. This whole board is designed with KiCad, and all the UI elements that you see are built with PyQt. PyQt Graph does all the plotting, SciPy and NumPy for analysis. You'll find the docs at KuttyPy.readthedocs.io. For Windows, I have a compiler installer built with PyInstaller. If there are people who do use that. Let's say KiCad drawing. I have it somewhere here. So KiCad is very powerful, very friendly to use, and this is the board that I was just showing you. And here, it's a nice 3D view of everything. And with this board, I think we trained about 2,000 students, 40 odd workshops, and I figured we'll make something more appealing for 8th graders. So we're working on a similar board, but it's in the form of a turtle, and it has motor drivers and it can sort of move around. So this is a SEM turtle, similar approach, but some sensors are already on board. There's a magnetometer on board because then the turtle will know which way it's pointing. So my plan is to implement the logo turtle, but in as a actual hardware, which you can command take 10 steps forward, take 90-degree turns, etc. I think I'll skip this. We're nearing the end of time, right? I'll skip the video. There is that's the turtle. It moves around. It can speak to other turtles. Very basic board, again, just like an Arduino, but has a bunch of things on board in addition. Yeah, that brings me to the end of my talk. These are the links for the different things that went into this. I think I'll take questions now. We're at 10:20. These are photos from the workshops that we've been conducting. It's the homepage. Docs. There's a workshop page on the docs for Nano. This was at Science Hack Day last couple of years back, and we had a whole setup for this. And that's the page on my personal website for the STEM turtle. I'll take questions. Thank you.
I heard about KuttyPy, I think, quite long back in PyCon India. Good to see it's kind of making so much progress. So one thing I didn't understand from the talk is where's the Python code running? Is it kind of running on the computer or is it running inside
the Python code is running on your PC, connected PC. So the hardware is very minimal. You have the bootloader, which is only about 500 bytes, the original OptiBoot bootloader. To that, there's a couple of function calls for reading and writing registers. That's it. Like you go to a certain location in the memory, read it, or you go to a certain location in memory, write it, and because that refers to a special function register, the hardware will sort of behave in a particular way.
So you basically converted that into an RPC server. Is that
sort of like debugging? Yes.
Yeah. You send, give me this and
fetch. Okay. That's it.
So why is it hard to do the same thing with Arduino without changing the bootloader?
Why is it hard to do?
I mean, why can't I do the same thing? Why do I need KuttyPy? Why can't I just kind of write?
No, you like I showed it in the beginning. You can take a Nano, just replace the bootloader, but the entire software stack, the Python library, allows you to plug and play sensors. It's already written the part for plotting data, so that stack is there.
Got it.
Right. So otherwise, if you wanted to read data from a particular sensor, you would write a firmware, a sort of state machine to upload to your Arduino.
Yeah.
Right. And then if you use it for some other purpose, you would have to replace your firmware again.
Yeah.
Here, this particular section sits in the bootloader, regardless of what code you're running, and you can switch to the bootloader and tweak and see if things are running fine, etc.
Thanks.
You said the tortoises talk to each other.
I2C.
Okay.
It's
Physical connection.
so this one I've used these RJ11 jacks where one leg can be broken off and you connect a cable from here to here, and you can use this as a sensor bridge, or you can connect this to the leg of another where one will behave as a slave and the other as a host, like a host client architecture. So here if you see the USB is not connected, it's listening over I2C through one of its legs. The cable is at one leg and just controlling one from the other. I don't think this 328P is, I don't know if they can. Well, I've not tried personally, but I don't know if it'll fit, especially the visual programming part. I am planning to explore it, at least for this Turtle board. I'm planning to have an ESP which will host a web server and the entire visual programming stack within a couple of megabytes. So then you just connect to your battery pack powered Turtle, and on your phone or laptop, whatever web connected device, you build the code for FT40, RT90, these things, to have like a logo Turtle which moves around. That's a future plan. So
Can we resume the questions after the other talks? Just